Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering, and we'll extend our discussion on thermal properties of materials. So far we have covered heat and temperature, and we discussed in a very I will say so far detailed manner about the basic concept of heat and temperature, because these two are the foundational stones, the basic foundation of thermal properties, which is basically derived from thermodynamics, but it has its application in material science and engineering for the selection of materials on the basis of their thermal properties. Okay, so now we'll go one step forward from that. We'll discuss a particular thermal property, which is heat capacity, specific heat, and water equivalent. They are basically same thing, but they are derived from one another. We can say it is it is the same property but expressed in different ways. Okay, so just to recap some basic concepts so that you are on the same page with me, just to recap. So basically, heat of an object, okay, any object, the heat content is basically the total internal energy content of that body. This is derived from the movement of the molecules, okay, the movement of molecules, and those movements are of three types, okay, translational, vibrational, and rotational. This leads to the kinetic energy of the molecules, and that leads to the internal energy content of the object. Now I said that the heat in itself of an object, the heat content in isolation, if you consider, then it has no meaning. It only has meaning when the heat is in flow, okay, when the heat is in transit, when the heat flows from one body to another, okay, one body to another, let's say from the first body to the second body. And what determines the direction of heat flow? That is temperature. So temperature determines the direction of heat flow, and heat always flows from a body which is at a higher temperature to a body which is at a lower temperature, till both of them they are at the same temperature, which is called as thermal equilibrium. So when heat flows away, the temperature of that body it decreases, and when heat flows into an object, the temperature of that increases, till both of them they arrive at the same common level, which is called as the thermal equilibrium temperature. That is, both the objects they have the same temperature now, and no longer there is any heat flow between them. So this much you are clear about now. So what is heat capacity? Okay, what is heat capacity? So the heat capacity, which is expressed mostly in terms of capital C, whereas different books can have different notations, but mostly it is capital C, which is the accepted way. So the heat capacity, capital C, of a particular object or a particular sample of an object or a substance or a material, whatever you call it, it is defined as the amount of energy, which is basically heat energy. When I say energy, it is heat energy, the amount of heat energy which is required to raise the temperature of that sample by 1 degree Celsius. Okay, to raise the temperature of that sample by 1 degree Celsius. So let us say we have an object, any object. Here the mass of it is not specified. There is no mention about what is the mass of the object. Suppose if I supply, let's say 4 joules of energy, okay, 4 joules of energy, and the temperature it increases by 1 Kelvin, okay, 4 joules of energy and the temperature increases by 1 Kelvin. So the heat capacity is 4 joules of energy, that is heat energy Q, which is supplied for a temperature increase of 1 Kelvin. So it is 4 joule per Kelvin. Or if we use this, this is not a a real example, I'm just giving this to make you understand. Similarly, let's say if I give, let's say 16 calories of energy and the temperature increases by 1 degree Celsius, the heat capacity in CGS unit, that is 16 calorie per degree Celsius. So here the mass of the object is not specified. That is an important point. Here the mass of the object is not specified. Whatever the mass of the object is, we keep supplying heat and we keep monitoring the temperature. So we see for a 1 degree change in temperature, whether it is in Kelvin or degree Celsius, how much heat is required. For every 1 degree change, how much heat is needed. So that is the heat capacity of that material, and it is expressed as C, that is capital C, that is equal to delta Q by delta T, where delta Q is the heat energy required, which is the heat energy supplied, and delta T, which is the change in temperature or the increase in temperature. Okay, and the unit is calorie per degree Celsius in CGS and joule per Kelvin in SI. Okay. Next, this is heat capacity. Next is a bit more specified. It is derived from heat capacity, but it goes one step ahead. It specifies something. So what was lacking in the previous thing? The mass of the object was not specified. So in specific heat, we go into the specifics. So the specific heat of a substance is defined as the amount of energy, the heat energy, which is required to raise the temperature of a unit mass of substance through 1 degree. Okay, so what is unit mass? That is 1 gram or 1 kg. Per grams, per kg, how much heat is required to raise the temperature by 1 degree, 1 degree Celsius or 1 degree Kelvin, depending upon which units you are using, whether it is CGS or SI. So let us say we take an object of unit mass. So here the difference is that mass is specified. Mass is specified. That is the difference between heat capacity, that is the difference between heat capacity and specific heat. Here the mass is specified. We take 1 gram of the substance or 1 kg of the substance, because these are the accepted units, SI and CGS. So per 1 gram, how much calorie of energy is required to increase the temperature by 1 degree Celsius? That is the specific heat in CGS. For every 1 gram of substance, how much calorie of energy is required to raise the temperature by 1 degree Celsius? Let's say, for a hypothetical example, let's say for 1 gram of substance, we require, let's say 20 calorie of energy to raise the temperature by 1 degree Celsius. So how much will be the specific heat? 20 calorie per gram per degree Celsius. Let us say for 1 kg of substance, I'm giving entirely hypothetical examples to make you understand. These are not in any way real world examples, okay? So don't confuse with that. So let's say for 1 kg of an object or a mass, we require, let's say 50 joules of energy to raise the temperature by 1 Kelvin. So what will be the specific heat? 50 joule per kg per Kelvin. Okay, this is the specific heat. Okay, this is in CGS, this is in SI. So specific heat, it is expressed as small c, and we can say that is the heat capacity per unit mass. So it is expressed as, if an energy of delta Q, when it is transferred to a mass m of a substance and it raises the temperature of that sample by delta T, then the specific heat of the substance small c is equal to delta Q by m delta T, where delta Q is the heat energy supplied, m is the mass of the substance, delta T is the rise in temperature, the increase in temperature. Because when heat is supplied, temperature will increase. And if you see here, this delta Q by delta T portion, delta Q by delta T portion, that is what? That is heat capacity. And this M is there. So this is specific heat, is heat capacity by mass. So as I said, everything is derived from the other, but we have to understand it separately, to get a better idea. So the unit is calorie per gram per degree Celsius in CGS and joule per kg for Kelvin in SI. Okay, so this is heat capacity, this is specific heat. Then we can go into more detail also. Let's say we involve the number of moles of the substance into the equation also. Okay, that when that is specified, the number of moles is specified, it becomes molar specific heat. So the molar specific heat of a substance is defined as the amount of heat required to raise the temperature of 1 mole of a substance through 1 degree Celsius. 1 mole defined by Avogadro's number. Okay, so 1 mole of a substance through 1 degree. So let's say for 1 mole of a substance, okay, for 1 mole of a substance, let's say 1 mole of a substance, we require 90 calories of energy to raise the temperature by 1 degree Celsius. So the molar specific heat is 90 calorie per mole per degree Celsius. So each mole requires 90 calories of energy to raise the temperature of that 1 mole by 1 degree Celsius. Similarly, if for the SI, if let's say for 1 mole it requires let's say 180 joules, again hypothetical examples, 1 degree Celsius, so it becomes 180 joule per mole per Kelvin. So for every mole 180 joule is required to raise its temperature by 1 Kelvin. Okay, so the molar specific heat is expressed as specific heat C, small c subscript m for the moles, the number of moles, that is equal to delta Q by N delta T, where delta Q is the heat energy that is required, N is the number of moles, and delta T is the increase in temperature. Okay, its unit is calorie per mole for degree Celsius and joule per mole for Kelvin, CGS and SI respectively. Okay, next is it is also an interesting concept. Sometimes for various practical purposes it is easier to represent everything, the heat capacity, specific heat, in terms of the water equivalent. Okay, so try to understand this. Because water is easily available, we can substitute this, water, with a particular substance to analyze it. For that purpose, comparative analysis, it is used. So let's say, the water equivalent concept, what basically it means is that it is basically the mass of water which requires the same amount of heat as is required by any particular body to to cause an increase in the same temperature level as the water. Okay, let me give you an example. Let us say we have an object, okay? The mass of it is not specified, but it requires delta Q amount of heat to raise its temperature by a certain amount of level, delta T, okay? As per the definition I'm going, okay? Delta Q amount of heat causes a temperature of delta T. Okay, let's go for numerics, okay? So let's say 40 joules of energy causes a temperature increase of, let's say, I will go for numeric, let's say 1 Kelvin. 1 Kelvin. So we have to find out an equivalent mass of water, okay? We will have to find out an equivalent mass of water for which if we supply 40 joules, it will also cause a 1 Kelvin change in temperature. Okay, so here the mass of this object is not known, it is unknown, but we have to find the equivalent mass of water for which 40 joules will cause a 1 Kelvin change in temperature. How much mass of water is necessary so that if we supply 40 joules, there will be a 1 Kelvin change in temperature. If we go for CGS, same thing, whatever calorie of energy is required to raise the temperature for the same amount in degrees Celsius. 40 calories for 1 degree Celsius or 80 calories for 1 degree Celsius, whatever it is. Units, units are interchangeable, but the concept stays the same. Okay, so this mass of water for which there is a same increase in temperature or change in temperature for the same amount of energy as this object, the unknown object, that is called as the water equivalent of that object. So we want to find out an equivalent mass of water for which the heat supplied and temperature change is the same as for the unknown object. Okay, known mass of water for unknown mass of object. So water equivalent is basically mass into specific heat, mass and specific heat of water. So if we, let's say, W grams or kg of water is there and the temperature increases by 1 degree, so the water equivalent is mass of water multiplied with the specific heat of water. Okay, so here we have discussed some important concepts related to the properties associated with heat and temperature. It is just one category, one layer. There are many layers to it. This is just one layer. Okay, slowly and steadily we'll uncover all the layers, going from basic to intermediate to advanced slowly. So don't worry. So this is about heat capacity. Specific heat is derived from heat capacity. Molar specific heat, again extending upon the concept of specific heat and heat capacity, and then water equivalent, which is basically for comparative analysis based on equivalent mass of water. Okay, so this is the